So, we on time now? Yes, we're on time. So, Angie's not here, and Benjamin's not here, and Brandon not here. Okay. Okay, they'll come in. So, before we really get going, I had a few things I wanted to say, but I'm kind of fuzzy in the head right now. So, let me start with a suggestion. I mean, if you're getting straight 100s and acing the exams, and you know who you are, you can ignore me. You can do whatever you want. But what I highly recommend if you're not is, you know, I think I told everybody on my website, I put my notes that I use for the class. And if you have a laptop, you should just go to that website now and follow along, so you're not just seeing me dance up here, perform, whatever. You can also follow along visually. I know that sometimes helps. Sometimes if you kind of, you know, you don't have to kind of focus needle point on me. You can kind of see where I'm going and keep up. I find that's helpful. So that was one thing. Another item. There'll be a quiz this coming Tuesday. Things that might be on the quiz are volume, average value of a function, length of a curve, and what we're going to do today, we're going to look at polar coordinates, and we're going to learn how to do an area in polar coordinates and the length. So that's what the quiz will be on. Okay. Any questions on the homework? I think there was some. Yeah.
Actually, I was just hoping to get clarification on the directions. On page 463 for number 7, on part C, it says sketch a graph of f and a rectangle whose area is the same. So
463, number 7?
Yeah, for part C.
Sketch the graph and a rectangle whose area is the same as the area under the graph.
So, I mean, like, let's say the area under f was 2. Do you just want us to draw like a 1x2 rectangle or something?
Well, I think they mean a rectangle over the same length.
Oh, okay.
So this guy, x minus 3 squared, so that would be kind of, here's 3, right? This. And they're interested in from 2, 3, 4, 5, right? So I think they want a rectangle with that width.
Okay. And then
This is kind of up on the board up there. Or let me fake it. Doesn't really look like this. So you would go, oh, well, the rectangle is, kind of like that.
oh, I got it.
The same area.
So basically, that would mean like for the rectangle, like the area.
The area under the rectangle is the same as the area.
Right.
Right.
Okay.
Which kind of fits into the idea of the average value.
Right. Okay.
Other questions on the homework?
Can you do number 12 on that page?
Okay. So 12 says, find the number b such that the average value of f of x equals 2 plus 6x minus 3x squared on the interval 0 to b. So they want the average value to be 3. Average be 3. So let's look at the formula here. It's 1 over b minus 0, 0 to b of interval 2 plus 6x minus 3x squared dx, right? And we want that to equal 3. I can go on. Is that enough for it?
Yeah, can you go on?
Yeah, sure. Okay. So this is 1 over b. 2x plus 6x squared minus x cubed from 0 to b plus 3. This is an equation, right? So 1 over b times 2b plus 6b squared minus b cubed.
Shouldn't it be 3x squared, 3b squared?
This should be 3. Is that what you're saying?
Yeah.
Yeah, that would be correct. Minus 0, right? So dividing through by b, we get 2 plus 3b minus b squared equals 3. Or you subtract, b squared minus 3b plus 1 equals 0. So that doesn't look nice. So we'll just use the 9 minus 4, 2. So 3 plus or minus the square root of 5 over 2. Okay, so now it would be a good idea to see what do those two different roots mean. So my graph, what does that look like? It's going to be an upside down parabola. I don't know where it starts. I'm lazy. I'm just getting lazy. Don't get lazy. You're too young. I guess this you could say I'm being smart. I don't know. so it sort of looks like this. And we're either integrating from 0 to about here somewhere. What would the minus be? Oh, well, that's kind of weird. I think I must have made a mistake here. Everybody agree? Let's go look again. So we want the average value of this to be 3. 2x. That's good. So 2b plus 3b squared minus b cubed. Those are all zeros. Over b. So it's 2 plus 3b minus b squared. Oh, wait a minute. Up. So change the signs. And you end up with b squared minus 3b plus 1. So that's 3 minus 9 minus 4ac 2.
I think you're right, because that's for numbers for B, like plural. The question is for numbers B to B.
Well, okay, there's no reason there couldn't be two answers. But looking at the graph, I find it hard to believe that. I mean, let's actually get some numbers here. So 3 plus square root of 5 divided by 2 is 2.61. And 3 minus square root of 5 divided by 2 is 0.381. So it doesn't make any sense that this area is equal to this area is equal to 3. So one possibility is that you get an extraneous root somehow. So it's possible. But I don't see how.
Wait a second. Oh wait, it's asking where the average of a function is equal to 3. So
Yeah, well, I'm finding the average. Right? Wrong one. Right? That's what this 1 over b minus 0 does.
Mhm. And there's possibly 2 places depending on where you are from the vertex, right?
I didn't understand. The vertex?
So if the vertex is to the right of the origin, then you can have a point going up to the vertex that can be a value, and there can be a value on the other side that has the average as the first value.
Oh.
Possibly.
Yes. That's, yeah.
Is the vertex there?
Well, the vertex is on the right side. But, yeah, I'm forgetting, I guess what I'm forgetting is they want the average value to be 3.
And there can be 2 points for the
So
average.
it could be that you get to here it's 3, and then you get to here it's 3 also.
On the other side of the parabola, maybe.
No. Well, yeah, maybe, yeah, that's true. Well, the only way to find out for sure, not the only way, is I could plug in that original equation, right? So 2 plus 6x minus 3x squared. And then I find the, okay, let's go from 0 to 0.381. And now I divide that by 0.381, and I get 3. So the average value here is 3. So let me try it again. Yeah, I'm just outthinking myself here. It just didn't. So I go from 0 to 2.61, and I get 7.87, right? Which I divide by 2.61. And it's about 3. So yeah, it just turns out, I guess what I'm not really looking at here, this is the function. I'm not thinking what does the average of the function look like across here. And I guess, what is the average? There's no way I can plug that in, is there? Oh yeah, I could plug that in, which is B, whatever, this guy. So it just happens to be that the average, what does the average do between here and here? Curious minds want to know.
I could try drawing it, I think.
B squared minus 3B plus 1. Oh, so what that looks like is get that right.
Remember to divide by B.
No, I've already done that here.
All right.
Oh, not equals 0. Just that. Well, yeah, equals that function. Yeah, it's where this equals 0. That's what I'm looking for. So the graph kind of looks like this. And there are 2 places it's 0. So between these two, I guess the average is less, and then on either side it's greater. Okay, it's just a quadratic function that has 2 roots. Okay. I don't know why I made a big deal of that. I mean, confused myself. I hope I didn't confuse anybody here. Okay, other questions on homework? Just Benjamin? Is Benjamin here? No. Oh, you are. Okay. All right. Everybody's here. Any other questions on homework? No? Okay. All right. Today, as I mentioned, we're going to talk about polar coordinates. Is there anyone here, please be honest, who's never seen polar coordinates? Everyone's seen polar coordinates. Good. You're supposed to have. And I can go over them fairly quickly. So instead of x and y coordinates, where we have an x-axis and a y-axis, we have our theta coordinates, they still kind of draw the xy coordinates. But now, a point on here, instead of having an xy coordinate, it has a theta and an r coordinate, r theta. How do we usually do that? R theta. There's some things to watch out for in polar coordinates. A polar coordinate for a point is not unique, and there are a few gotchas. For example, any point with an r of 0, say r0 theta 1 and r0 theta 2, is the same point. We're going to do an example later where you're going to see two curves that intersect in 3 points, but if you try and solve for it, they only seem to intersect in 1 point. In 2 points, and that's because the third point is something like this. They are the same point. You also have that problem of going around in circles. So, for example, the point 1, 0 is equal to the point 1, 2 pi. That's a little easier to detect. You're not really interested in theta. You're interested in kind of theta modulus 2 pi. And then finally, you get some really confusing stuff where you've got the radius going in the opposite direction. And there, like in this example, so here we have kind of 1 with 0 degrees, but -1 from pi. It's the same thing. So you want to be aware when we're dealing with this. Sometimes funny things will happen. Okay, very important. We need to know how to convert to and from polar coordinates to Cartesian coordinates. Use this diagram again. So if you have r and theta, well, you have a triangle here, and we use our trigonometric functions, and you can see that x is r times the cosine of theta, and y is just r times the sine of theta. This is going from polar to Cartesian. Do you know where the word Cartesian comes from?
Descartes.
Descartes, yeah. Just cut off the beginning of his name, I guess. Okay, if you want to convert back, you're starting with xy Cartesian coordinates, and you want to go to polar. How would you do that? Well, r you can find by using the Pythagorean theorem. Theta is a little tricky. So in general, theta is equal to the inverse tangent y over x. If x is not equal to 0, of course. If x is equal to 0, what happens then? Well, you've either got a point at 0, a point up here, in which case it's pi over 2, or a point down here, in which case it's 3 pi over 2.
Can you put the other board back up for a second?
However, it's still a little more complicated. If you remember, the domain of tangent inverse is minus pi over 2, pi over 2. So that's just the first and the fourth quadrant. So you certainly can have points in the second and the third quadrant. How would you know? Well, you have to look at x and y. Think about it. If x and y are both positive, of course, it's the first quadrant. If it's minus and plus, it's the second. First quadrant. Now, what do? You know, this gives you a theta which is not in the first quadrant. Let's come in kind of do an example. So you have a point here, and instead of getting this angle here, what do you get? You get this angle here, right? So I'll call this negative p, right? So if it's really it's not in the fourth quadrant, it's in the second quadrant, what do you have to do? You have to add pi to it. So in this case, you would add pi. If they're both minus, you're going to get a value in the first quadrant, but you're really in the third quadrant. So again, you have to, should be in the third quadrant, you have to add pi. And likewise, in the fourth quadrant, you're good. Just like the first. So that's as far as this conversion. I don't know why I'm mentioning this, but I thought it was interesting when I started computer programming. They often give you, sine function, cosines, inverses. But they had this function inverse tan xy, where you give it both coordinates, and that's just so the computer function can return to you the right angle. I guess, maybe we need a special, on our calculators, a special function, we'll call it what they call it on the computer, tangent 2 inverse. And you feed it an x and a y, and it gives you the right angle. Make life easier. Okay, so next question. What is a polar equation? An equation with polar coordinates. Well, let's look at a few. R equals 5. What would that be the equation of? Anybody know? I have my polar graph paper here. Right. What's this an equation of? R is always 5. What have I got on my graph? It's a circle, right? Just a circle at, say, here's 5. Okay, it's easy. How about something like R equals theta? That's not so obvious. I mean, it starts at 0, right?
Isn't that a spiral? Spiral? I guess theta increases.
Yeah. As it increases, theta increases, R increases. I kind of ruined my diagram here, so I'll just draw it again. This is actually a special kind of spiral. well, I'm not going to be able to differentiate them. There are two of them. One of them is called an Archimedean spiral. I think the other is a Bernoulli spiral. I think this is a Bernoulli spiral. No, actually, I think his is the other one. Equation is kind of R equals A to the theta, where it's kind of, kind of exponential. This is, I think, the kind of spiral you see in a seashell, right? Or in nature.
It's the Fibonacci sequence, this Fibonacci spiral.
Yeah, Fibonacci spiral, if you like. Okay. All right, one more. Let's do one more. Does everyone have a calculator today? Does anyone not have a calculator? I have. Who will need a calculator? Calculator, Angie? You have a calculator? Okay, if you don't have a calculator, kind of shove over to somebody you like who has a calculator. Maybe you're all aware of this, but if you click Mode on your calculator, make sure your radian degree is on radian. We're going to be using radians, but right below it, you'll see something that says Func, Par, Pol, Seq. Anybody wants to, give the professor an apple, can stay after class and tell me what Seq does, but Func is what we usually use. Par is parametric. I think we've done a little parametric equations, but the third one is Pol is polar. So if you click on that and you go to Y, you'll see that now your function is R1 equals. So everybody try R1 equals cosine of theta. And take a look at the graph. And if you're in my shoes, you want to zoom in. And actually, you might want to say zoom square, because otherwise you might get fooled. All right, what do you see? Oval. You see, you didn't do square. If you do square, zoom square, you'll see that that oval is actually a circle.
Okay, a circle, yes.
What you should see, it looks like. As best I can draw a circle. That's R equals cosine theta. I'm just thinking, if you go back to those conversions, as far as square root of x squared plus y squared, so the square root of x squared plus y squared equals cosine theta, so x squared plus y squared equals cosine squared theta. Should that come out as a constant? Oh, no. You have to, okay, never mind. I just got carried away. Okay, since you've got your calculators already, I'd like you to plug in r equals 1 plus cosine theta. Take a look at that. So we just say insert 1 plus, no, it didn't work, cosine theta. So what's that? Do we know the name of that guy?
Carboid.
Carboid? That's how you pronounce it.
I was saying cardboard at first.
Yeah. Something like that. That's heart-shaped. I think it comes from the same Latin root, I think. Okay, has everybody done that? Everybody happy? Cartoid? Okay, let's try one more for fun. Cosine 2 theta. You get that? You could probably have fun with this all day, right? Just creating funny things. Whoa, who said that? What would you call that?
Well, it's one of the foils, the quadrifoils. Quatrefoil.
Oh, I don't know the name. It's kind of a clover shape. You should get something like this. Kind of reminds me of, it's not what it looks like, but if you're doing chemistry and you're looking at orbitals, kind of look like that. If you're not getting the whole thing, then what you want to do is look in your window and look at your limits on theta. So if you just said, you know, like, say, theta from, say, 0 to pi, you would just get a part of this. You actually have to go around and around and around and around and around. All right. And then just a little bit more, I guess we'll call it polar review. A few things, a few little useful but tricky things you should know about polar coordinates, or polar equations and polar coordinates. You have some r equals f of theta, and it turns out that f of negative theta is equal to f of theta. There's some kind of symmetry going on there. And that would be symmetry along this x-axis. So, for example, in the first case, we did cosine of theta. Since it's a circle that's symmetric around the x-axis, you would expect cosine of minus theta to look the same. If, on the other hand, in this equation, you can substitute minus r, or I guess you say r equals minus f of theta. If that equals f of theta, you've got a different kind of symmetry. You have a symmetry around origin. So this would kind of swing over here. Actually, this point would come down here and so forth. So that's a different kind of symmetry. So I guess this is the x-axis. This is the origin. And then finally, if you find that f of pi minus theta is equal to f of theta, then it's just like this symmetry, except it's around the y-axis, right? So something was over here. If something looked like this, then it would have a symmetric part over here also. And just something, when we're going on to the next step, we have like an even function. Sometimes we can simplify the integral. If we have an odd function, sometimes we can simplify the integral. Any questions up till now? That was just what I call the review part. And the next part is the calculus part. Okay? Ready? So what we want to do is, given a function r equals f of theta, we want to know how to find the area over some interval a to b. So we're going to start looking at something really simple. If I have a circle, radius r, we know the area is what? Pi r squared. So now, let's say I take a section of angle theta. I want to know what the area of this sector is. But I want to explain it in a way that you could reproduce it pretty easily. So let's say this sector, right, goes all the way around. It's 2 pi. Theta equals 2 pi. Then what's the area? It's pi r squared, right? So if theta is just a fraction of 2 pi, right, then the area with respect to theta will be pi over r squared theta divided by 2 pi. Is that clear? In other words, if it were 2 pi, this would just cancel and you get pi r squared. Okay, but we can simplify this, of course. Pi's drop out, and we just get r squared over 2 times theta. So that's the area of the sector. So the idea here now is we have some function that goes from, say, angle A to angle B, and we have some f of theta. So what we're going to do is we're going to break this up into little tiny pieces, little tiny sectors, and we're going to approximate them by using the formula for the sector. So if you think about this, you have like the sum. I'm actually going to write out the sum. So have points A, x1, so we have 2 theta. Theta 1, theta 2, theta n minus 1, and then B. So the radius is f of theta, so we would say theta 1 minus a squared over 2 times theta minus 1, theta 1 minus a, plus f of, now we've got theta 2 minus theta 1 squared over 2 times theta 2 minus theta 1, all the way to the end. So we have this sum, and now we just add more and more points so that these sectors are better and better approximation of the area. Well, you know what happens when you take a sum and you let the kind of the size between these go to 0, you get an integral. So the integral is just going to be the integral from a to b of f of theta squared over 2 times our little infinitesimal amount of theta. And that should give us the area of this function. Now, you do want to be careful here. If I had a function like cosine, right, and I integrate it from 0, say, to 4 pi, what's going to happen? Well, I'm going to go around once, and I'm going to go around twice, and I'm going to add up the area twice, which isn't really what I wanted to do. So you do have to be a little careful about the limits we're using. All right. Any questions about this so far? It's kind of the real meat of what we're doing today. All right, let's do an example. I'm going to take an example we used before. R is cosine 2 theta, and I want to integrate it from minus pi over 4 to pi over 4. So again, if you have your calculator handy, you might want to try this, but again, minus pi divided by 4 and pi 4, and what you should see on your graph is that it just kind of goes like this. It's just one piece of it. So we want to find the area inside here. So using our formula, we want to go from minus pi over 4 to pi over 4. Our function is cosine 2 theta. So we want to square it and divide by 2. And now we just want to find this integral. So at this point, this should be fairly straightforward. Cosine squared 2 theta is cosine 4 theta plus 1 over 2. We've already got over 2, so it's 4. And I think we'll go sideways here. integral of cosine 4 theta is going to be, the antiderivative is going to be sine 4 theta over 4. So this is over 16 plus theta over 4. So what do we get here? Sine of pi is 0 plus pi over 16 minus
0,
sine of negative, 0 again, minus pi over 16. So we got minus minus, so it's just pi over 8.
Let's see.
That was easy. So a lot of these are easy. Some will not be so easy. Questions about anything? Yes.
I was asking about the homework. The H1 and H2 are like homework 1 and 2, right?
Oh yes,
Or there's
when you look up the homework assignments,
3?
don't get thrown in the back of your book. You'll see Appendix H, H1, and there are problems from the end of each of those sections, H1 and H2. That's also where you'll find the material we're looking at. Yes?
Why do you square it and divide it by 2 again?
Okay. I think I erased this. Okay. It goes back to what is the area of the sector, right? So we know the area of the whole circle is pi r squared. So per theta, it's pi r squared theta over 2 pi, which when you simplify is r squared over 2. That's where the function squared over 2 comes from, right? In other words, we're looking at a function as kind of an, infinitesimally small angle here, and we're adding up its area, with our integral. And instead of r, the function, in other words, this is a function whose value is r. It's a function of theta, right? So in the problem I just did, r is the cosine of 2 theta, which varies. But if we take an infinitesimally small piece, this area, r squared over 2 applies. R squared over 2 times the infinitesimal angle. Make sense to everybody? I mean, it's just a, it is just a formula. You can use it kind of dumbly, but it helps to understand where it comes from. Okay, other questions? All right. Let's do a hard problem. There's a hard problem in the book. We're going to go over that. Hard problems sometimes take more paper or board space, right? So we'll clear a little off. All right, so the problem is find the area that lies inside the circle r equals 3, and outside the cartoid r equals 1 plus sine of theta. Doesn't sound right. sine theta. Okay. So, picture's worth 1,000 words here. This circle r equals 3 sine theta is just a circle with radius 3, sits on the origin, and center is out here. And this cartoid kind of looks like this. So it's going to intersect at 2 points. And we want the region inside the circle, but outside the cartoid. So we're going to do kind of 2 integrals here. We want to find, well, we want to find the area inside the circle from here to here, and we want to subtract out the area of the cartoid from here to here. So really, what we want to know is where do these intersect? So how are we going to figure that out?
Set them equal.
Yeah, we're going to set r equal. So 3 sine theta equals 1 plus sine theta. So 2 sine theta equals 1, or sine theta equals a half. Or theta equals sine inverse a half. Okay, so sine inverse gives you an infinite number of solutions, right? So we're going to have to look at them a little carefully. Remember what have a sine opposite 1/2 over the hypotenuse, right? Remember what that angle is?
5 over 6.
5 over 6. This is a 30, 60, 90 triangle. So one of the solutions is pi over 6. And of course, pi over 6 plus 2 pi, n, right? There's an infinite number of them. What's the other angle?
5 pi over 6.
5 pi over 6. That's the supplement. Yeah, the supplement. Okay, let's do a reality check. Does that look right? So we kind of have something here. I guess my diagram isn't quite right. It should be smaller, but that's my pi over 6. And over here, 5 pi over 6. So, okay, good. I want to integrate clearly from pi over 6 to 5 pi over 6. And I want the area of the circle included, right? So what do I do with 3 sine theta? I square it and divide by 2. And that will give me the area within this kind of ice cream cone shaped thing here. Now I want to subtract out the cartoid. So I'm going to subtract 1 plus sine theta, again, squared over 2 d theta. Okay. That doesn't look too bad. That looks like something we've been doing. So let's spill this out a little. So that's 9 sine squared theta over 2 minus, do a little algebra here, sine squared theta over 2 plus 2 sine theta over 2 plus 1/2. Okay. So 9/2 sine squared minus 1 is 8/2 is 4. So just have 4 sine squared theta plus sine theta plus 1/2. So does anyone remember what we do with sine squared theta?
1 minus cosine squared theta.
Okay, good. Cosine, I'm sorry, say that again?
1 minus cosine squared theta.
Is that 1 minus cosine squared?
Yeah, that doesn't help me any.
Or you can do a 1/2 times, one
Here, this is
cosine.
cosine squared theta equals, I'm sorry, cosine 2 theta equals cosine squared minus sine squared, or 2 cosine squared minus 1, or 1 minus 2 sine squared theta. So now I can solve for this, right? Cosine squared theta is going to equal 1 minus cosine 2 theta over 2. All right? I think so. So times 4, so we're left with 2 minus 2 cosine 2 theta plus sine theta plus 1/2. Well, 2 plus 1/2 is just 5/2. So now we can find the antiderivatives. 5/2 theta minus, this is going to be sine, right? So sine 2 theta. But we have to divide by 2, but we have a 2, so we can just leave that alone. And then this is minus the cosine of theta. And what were my limits? Pi over 6, negative pi over 6, pi over 6. Okay. So we have 5/2 pi over 6 minus the sine of pi over 3. Minus cosine of pi over 6. And then minus 5/2 pi over 6 minus the sine of minus pi over 3 minus cosine of minus pi over 6. It's tiring, isn't it? Okay, so this is just gonna, these two are just gonna add. So they're gonna be, can't really do this the way I want. 5 pi over 6. It's the sine of pi over 3. Let's see. Well, we subtract it here. We add it here, the sine of negative pi over 3, but that's the opposite, right? So these two just cancel, so I don't really have to figure that out. So I just need to know cosine of pi over 6, because I'm going to end up, that's going to be the same as the cosine of minus pi over 6. Right, this is just the same. Wait a minute, did I do that wrong? This is minus, this is plus, this is plus. No, that's plus. Right. So those go away. Nobody's paying attention. Who's going to help me here? It's one or the other. It's either 2 of these or 2 of these. I think it's 2 of these. I think you just subtract -2 cosine pi over 6. Okay. All right, that's a hard problem. I'm getting confused. Oh, there is one totally unrelated to the answer. There's one interesting thing about this. Remember when we were checking to see where these meet? You notice we didn't get the origin out of here, did we? They clearly meet in the origin. But where?
I think the issue is 1. Theta is probably different.
Well, look. If theta is 0, then r is 0, right? So that's the point 0, 0, right? You plug in 0 here, you get 0, and it's 1. So they don't meet at 0, 0, because this is at 0, 1. But if instead you plug in 3 pi over 2, what do you get? You get 0, right? Remember when I said that these are not unique? This is the same point. It just doesn't, doesn't look like it. That's why they can meet over here. Okay. Let's try some examples. First 3. And then we'll take a break. Or you can take a break now. Ooh, that looks so good. That's that TI-89, huh?
Yeah.
Did I give you one? No. Yeah. Okay. I guess that might be part of the marketing. You have to make, not only does it have to do more, it has to look better. When people want it.
Give one.
Anyone? I think I'm just going to write that formula up. Area equals integral A of B f of theta squared over 2b.
Yeah. Iron. Iron Friday. Oh, right.
Okay, would someone like to try number 1 on the board? Oh, was that a yes? No.
What, Sugary?
I thought Catherine, I thought
No, I heard it from here. I heard it from here.
But I saw enthusiasm, that's all.
So I saw it right here.
Okay, Matthew, you want to go up and point to the board? Is that what yours?
No.
No?
You can certainly point at
Some brave individual.
Give it a shot.
Oh, good. Remember, what I told you the first day about math, you have to be a little brave sometimes, you know? By George Brandon, you've got it. Now all you have to do is work your way through that integral.
Easier said than done.
Oh, it's not that word. You know, just because I skipped steps on the board doesn't mean you have to. You can write as much as you want. Well, the derivative of what is the cosine?
Sine.
Yeah, so you know it's going to be a sine, right?
Yeah.
And it's going to be sine 6 theta, right?
Oh, never mind. I just didn't think that. Because it's 3, 2.
No, you did it right.
Okay. All right.
Very nice. We want to take a look at that and see if you follow along. It was okay. Is there someone else who wants to show great bravery? There. No theater majors who want to get some practice in front of an audience? Uh-oh.
Daniel's a theater major, aren't you, Daniel?
Nope.
I don't know if I can do number 2. Give it a shot. So, r equals tangent to theta from 0 to pi over 8. So we're looking at the integral from 0 to pi over 8. Tangent squared to theta over 2 theta. Okay, that's it. Find a tangent. Integral tangent squared. I bet there's got to be one of those. I've forgotten it, but I bet there's got to be one of those formulas, right? So, like I said, the tangent of 2x. What would that be? Isn't that like tangent squared x over not here. well, you know, here's the ultimate cheat, right? See if it comes out to be some number that I can identify, right? Tangent 2x squared divided by 2. You can do this on an exam if I don't tell you what it was, right? Oh, wait, I'm in the wrong mode. Gotta get out of polar mode. And 2x squared 2 0 2 oops. Calculate. No, it's not identifiable. Maybe.
Could we do sine squared 2 theta divided by 2 theta?
You could, but that'll get you into trouble, I think. I think actually, probably what you want to do,
1 plus secant theta?
yeah, I was going to say,
Oh, there
That
goes
sequels
my
my
problems.
how does that work? I always forget. Tangent squared is
secant
sine
squared
over
minus 1.
cosine squared, right? So, plus cosine squared over cosine squared equals 1 over cosine squared. So tangent squared tangent squared plus 1 equals secant squared. So this is secant squared minus 1/2. And that secant squared has a nice integral. Tangent. So it wasn't that hard. I'm just getting lazy. Okay, so what's the tangent of pi over 4? 1. Correct. Plus pi over 16 minus tangent of 0, that's 0, plus 0. So 1/4 plus pi over 16. The only thing that bothers me about that, oh, minus. Minus, that helps. Oh, that looks like the number I got. Okay, actually number 3 is kind of like the one I did. So if you want to do that for practice, welcome to. But we're going to go on, because we have one more thing we want to learn how to do today. Which is actually, first it's straightforward, then it's tricky, then it's straightforward. Okay? So what we want to do is find out how to find the length of a curve using polar coordinates. So we have, again, we have some function r equals theta, function f of theta, and we have some interval. We want to know how to find the length. Well, we already know how to do the length, right? Recall that you have some x equals f of t, y equals g of t, that the length from a to b is just the integral from a to b, the square root of f prime of t squared plus b prime of t squared dt. You might recall we did this before. What we're doing is we're using the Pythagorean theorem, on some function, and we're adding up the distances between the points. Well, we just need x and y, as functions. So how are we going to do that? Well, we know that x is r cosine theta, which means f of theta cosine theta. And y is r sine theta, which is f of theta sine theta. Try not to confuse this f and this f. Maybe I should have used a different letter by h. H. So we need to find the derivative of these functions, square them, and find the integral under the radical sign. That's a lot of work. We're going to do it. All right. First of all, what is dx d theta? We're going to find the derivative of this. So it's a product. So it's f of theta times the derivative here. So it's negative cosine theta plus, negative sine plus f prime of theta cosine. And dy d theta is the derivative here, so it's going to be f of theta cosine of theta. By the way, there's going to be a lot of work here. It's going to get very confusing, and then everything's going to drop out. We can all be happy. So then we have f of theta. It's going to have a happy ending, so don't get scared or cry or anything. Okay. So now we have to take each of these and square them. We're going to need a lot of room for this. Bring down the second board, I think. By the way, this is a great exercise in algebra. Okay, let's square the first one, right? So we get f of theta squared sine squared theta plus 2, there's a minus sign here, minus f of theta, f prime of theta, sine theta, cosine theta, and finally f prime theta squared cosine squared theta. Okay, so that's the first piece under the radical. I guess I could kind of draw the radical this way, right? So the second part is f squared theta cosine squared theta. This time it's plus 2 theta, f prime of theta, sine theta, cosine theta, plus f prime theta squared sine squared theta. The radical doesn't have to be that. Okay, does everyone see what's going on here now? These two are opposites. We can just cross those off. This is f squared plus sine squared, f squared plus cosine squared. Sine squared plus cosine squared is 1. So we've just got f squared theta. And again here, f prime squared theta times sine squared and times cosine squared. Cosine squared and sine squared is 1. So it's just f prime theta squared. Well, that's beautiful. That is really beautiful. So our length from A to B is just the integral from A to B of the square root of f of theta squared plus f prime theta squared d theta. Could life be easier?
Yes.
Well, yeah. You could be a home ec major, right? No offense to home ec majors.
Can you run it?
Yes? What do I need to do? Bring oh, you didn't get that all down?
No. Thank you.
Okay. It's on the web.
Oh, okay.
My notes. It's a good exercise. It's like, wow, there is justice in the math universe. It's a nice simple equation. I guess if it didn't turn out to be a nice simple equation, we wouldn't be learning it. Okay. So let's do an example. Now, I love this again. This example is from the book. And they picked an example actually really interesting for a crazy reason. But let's find the length of a cartoid. Cartoid, I-O-D. R equals 1 plus sine of theta on the interval 0 to 2 pi. So this is the whole length of this cartoid we've been looking at. So f of theta is 1 plus sine of theta, and f prime of theta is equal to cosine of theta. So the length, the integral from 0 to 2 pi, the square root of this squared, which is 1 plus 2 sine theta plus sine squared theta, and this squared plus cosine squared theta. Well, again, this is going to simplify, and we just have this nice little integral 1 plus 2 plus 2 sine of theta. Then they go on and say,
Oh,
No, just do it with your calculator. Okay, all right, do it with our calculator. You come up with 8. Why am I so exercised about this? If you try and do it the hard way, something very funny happens. They suggest you multiply it by this fraction. They don't do it, they just suggest, oh, you could do it that way.
Oh, conjugation.
Yeah, okay. Well, that's really great, because what you end up on top is the square root of 4 squared minus 4 sine squared, which is 4 cosine squared, which is just on the top you get 2 cosine theta. And now you have 2 minus 2 sine theta. You can integrate this between 0 and 2 pi. And they don't do it, and I know why they don't do it. It's because they're chicken. See, what happens here? Well, at pi over 2, what happens? It goes to 0, yeah. Oh. That's really funny. You should graph this. You should graph this and take a look at it. Because it's at pi over 2, this is 0 also, right? I don't know if we've got into it in that much detail, but when you're doing an integral on some function, it has to be continuous on the open interval. It doesn't actually have to be defined in the endpoints. So you could try and do it this way, plus pi to 2 pi. But you're going to run into trouble. There's something weird happens here where the sign reverses. It's very weird. Anybody who wants to write it up and do it, I'll give 2 points. It's like a paper. It's like you're writing a paper. You integrate this definite integral, and you're going to do it by multiplying by this, what was that word?
Conjugate.
Conjugate. And if you can make it work out, I'll give you 2 more points. Because it's a hard problem, and your eyes will bulge before you're done. Okay, so we have 2 more problems you can try. How much time have we got? Oh, we've got plenty of time, don't we? Yeah, 4 and 5. You would go ahead and try 4 and 5. They should not have that property of being crazy, but you can do it with your calculator and see if you can shortcut. That's fine too. Do we have any questions for you on this? It's a nice little formula. You can use.
How do you understand? What? My parents use the grandma's Japanese. Yeah, but she speaks.
No, but we have classical Greek and that, but we know actually.
Yeah, so that's why I said like 3:30 now. 3:30 to 4, I don't know. I have a pretty good. I can't talk about that super.
If I could work, so I call it service and
No.
oh yeah.
Does anyone know who Rendi Watulindus is? Anyone know Rendi?
I think that's in another class.
It is. I know everyone in this class. Or he.
Oh my god! Oh my god! I mean, in the class in the 6 to 8 o'clock one. In what's his face and stuff.
Yeah, I don't know. It's weird. It's been here for weeks. It's hers or his. But I do a good deed if I could. Is that bad? You're scratching your head? Does that mean?
Oh, no, just.
Oh, it's itchy head, okay. I mean, sometimes when people are working really hard, they literally go like this. Doesn't help, but
Well, actually, maybe I should be scratching my head anyway.
maybe it helps.
Yeah, maybe it stimulates the neurons.
Right, yeah, if you have any.
Probably not on the
Eating is good too, because you give fuel for the brain cells, right?
Exactly.
Start moving on to read over class or something.
I'm sure, when I was growing up, they used to say fish is brain food. I don't know why, I mean, maybe.
Yeah, that's what Asians say about the eye. Fish eye.
Oh, the fish eye is brain food?
Yeah.
Not the fish brain. That would actually make sense, even though it's stupid. Fish eye.
No offense, but I'll pass.
Yeah, I never ate that.
With,
Yeah. I think that's good.
Okay. So you want to do 4, right? You're done, right, Diana? No. No? You scared?
Yeah.
Oh, okay. Well, I guess
Don't be scared, you can do it.
yeah, I can't. You know, if like we were PhD students, I could say, well, you're going to have to give papers, so you need some experience. But nah, and you're not a theater major, right? So, where are you?
I'm sorry.
You're not a theater major, right? So you don't need experience for the audience. It's really easy as long as you're willing to make a fool of yourself, right? That's what like comedians have to do. Someone. Number 4. It's the easy one. I think it's real easy. I think it's real super easy. That helps. Actually, I don't really know. Somebody want to try number 4? I know Daniel wants to.
Whatever. I
Oh.
know part of it.
Oh.
I don't know the rest because I don't know
Okay.
if it's tangent or secant substitution at that point, but.
Number 4.
Number 4? I don't think we're talking about the same one. Did I label 2 of them 4?
No.
No. Okay. All right. Well, let's see how it goes.
Okay. I'm just gonna guess when it comes up.
Okay. So that's our spiral again, right?
Because after this one, I completely forgot what the 62 were. So, something. Yes.
Could use that.
Okay. But I was there is obviously tangent substitution, but I don't really
Oh, yeah, theta equals tangent, so you get secant. Well, you could do that. Tangent squared is, wait, the derivative of the tangent.
Oh, wait.
Root of the tangent is the secant squared, right?
Yeah.
It's on that piece of paper.
Eventually we'll get to there. No, I should probably do something else for this.
I guess it wasn't so easy.
Defeat.
I guess, no offense, but it is confusing to use the same variable.
Oh, wait, whoops, I keep on using
You can use x if you want to use x too. It wouldn't hurt.
This looks cool.
Okay. I'm really confused by what you did. And over on the right,
Oh, wait, it's 1 divided by secant squared.
no, you're saying like phi equals, you're saying theta equals tangent of phi, right? In the upper right-hand corner?
Wait. Now, this?
Yeah, you mean theta equals tangent of phi.
Yeah.
I'm trying to help. So that would mean d theta equals secant squared phi d phi. Right? You fired him. It's your fault.
You gotta lose your job for this week.
Take out his paycheck.
Yes. See if that. Well, where does this 1 over secant squared come from? Your audience is walking out on you here. So why is it 1 over secant squared? D theta equals secant squared x, right? So yes, okay. So now fix that. I think you're on your way. You could cheat on this one too, probably. Oh, they don't have secant to the end, do they? You could just use that if you want. But I think you would have been better off using the original, u squared plus 1. That's on the first page, I think. Well, I mean, if we're going to cheat, we might as well save time, right? All right, this is just straight out of the list at the back of the book. But don't mix up your u's and your thetas. You're either writing a u or you're writing a theta. Still have a u up there. On the left, you have a u. Have a theta. Oh, is that a?
Yeah.
Okay, okay.
So you see integrating by
Is that theta plus 1 there? Or is that theta squared plus 1? Right? Yeah. That was an easy problem. I was wrong. What an ugly answer.
Yeah, it's something.
Zero. Okay. All right, so this is sometimes what we're, thank you. This is sometimes what we're left doing when we get these weird integrals. You know, thankfully, this can be done in closed form. But, you know, the alternative would be to, you could, you know, if you needed to find the answer, you could use a calculator and use mechanical integration here.
Numerical.
All right, are there any questions about this length of a function in polar coordinates? It's just again, it's just doing the integration is the hard part. All right, I'm gonna hang out here for a few more minutes. Do you have any other things you want to talk about in here? One last thing. If anyone would like an answer key to the midterm, send me an email, and I will send you a copy. Diane, is that helpful?
Yeah.
Or you haven't had a chance to look at it yet?
Yeah, that's helpful.
Okay.
Don't look at it.
What?
Extra credit for a long time ago. Well, we're gonna tell I leave, so we can't like comment about it at home.
I just want to see what you're talking about. I'm not sure.
Look at this.
Oh, isn't it a little late for that?
I thought you said we could turn it in the numbers.
Homework, yeah, that's an extra credit. I'll look at it.
Oh, okay, I don't want to turn it in.
Turn it in. You're not going to take off.
Will you add?
If there's a reason to.
Okay. Okay, let me go first.
I guess I should, now that everyone's left, I'll say that extra credit I just gave, assignment I just gave you, you only have a week. Yes, questions?
And that's recorded, so. Would you be able to tell me how many you have to turn in?
Yes. I will. But first I'll turn this off, so